Hello, welcome back. Okay, so today we are looking at section number 15. And section number 15 is on pages 187 of your test. Okay, pages 187 of your test. Okay, are you there? All right, just flip over to pages 187 and let's get this discussion going. All right, get ready. Now, by way of information, let me say that section number 15 will be in 3 separate videos. So I'm going to make 3 separate videos for section number 15. And we will look at pages 187 to pages 191 will be the first video. And then pages 192 to 193 will be the second video. So in the second video, we will just be looking at the empirical rule. And then the last video will be from pages 194 upwards. All right. And that will just cover z-scores and percentiles. Is that okay? Nice. So this section number 15, we look at normal distributions. And I'm sure you are asking if there's a normal distribution, is there an abnormal distribution? No, actually, this is a very important concept in statistics. Okay, if you do statistics, you realize there are a number of distributions. We talk about the Poisson distribution, the Chi distribution, and a number of distributions. But for the purpose of our discussion, we will just focus on the normal guy. All right. So, and we are going to look at histograms basically. All right. And now we can use histograms we discussed in the last activity to determine his symmetrical data. So if you remember, we looked at left skewed and right skewed. Now, let me differentiate between a histogram and a bar graph. So remember, we are going to do that in the next slide. But so this is what a histogram looks like. All right. And this is a typical bar graph. So we'll be looking at a histogram, right? So a histogram is a bar graph, but not every bar graph is a histogram. And this is just a typical bar graph. So we have the x-axis and the y-axis. All right, but for a histogram, there are no spaces in between the bars of the distribution. All right, so we'll be looking at histograms basically. So you remember we looked at skewed left, and we said that and we will look at that diagram specifically. Okay, let me just wait when we get there. We'll talk about it, but this is just a reminder. Now, bell-shaped data follows a unique rule called the empirical rule. All right. Now, to use this rule, you will learn about standard deviation, which is a measure of how data is dispersed around its average. Now, we will expand on the 68, 95, 99.7 rule by calculating the z-score for a bell-shaped distribution. All right, so these names will be used interchangeably. So when you hear a normal distribution, a symmetrical distribution, okay, and a bell-shaped distribution, they mean the same thing. And then using a standard normal to find probabilities associated with that distribution. We will also define and use z-scores to find percentiles, and that will be in the third video. Okay, so these shall be our learning objectives. All right, so the following shall be our learning objectives. Now, so a histogram is a diagram consisting of rectangles whose heights are proportional to the frequency of a variable and whose width is equal to the class interval. All right, so I drew a histogram a while ago. Now, class intervals are needed when working with a continuous data set, like age, which can be represented on a number line. Imagine having a rectangle for every possible age. There would be over 100 rectangles. Now, dividing the possible ages into class intervals makes the diagram more manageable. Okay. Now, there's no distance between the rectangles since all ages are included and no age is excluded. So that is for a histogram. Note, all histograms are bar graphs, but not all bar graphs are histograms. Bar graphs can be used for variable with non-numerical categories. So for instance, if you are talking about age, which is a continuous data, right, we use a histogram. And when we are talking about individual items, so for instance, if we're talking about the items in Walmart, so we want to know quantities in Walmart. If you say the number of, say, tomatoes, the number of garden eggs, the number of fishes, the number of bread. Now, these would take individual bars. You cannot put the bars side by side. What do you call it? You cannot put the bars closer to each other. That cannot be represented on a histogram because these items are what? Individual items. Okay, nice. Now, so here we look at age distribution of the population. Is that okay? So we have the age distribution on our x-axis, and we have this is the frequency in thousands. Okay. Now, why is it appropriate for the bars in the graph to be touching each other? Now, we are not comparing separate items, but rather a set of continuous values separated into groups of 5 years. So that is why the bars are touching each other. Now, make a few observations regarding the shape of the distribution. Where are the baby boomers on this graph? So baby boomers are kids, people who were born after the Second World War, right? Now the bars, the taller bars, 45 to 49 and 50 would also include 60 to 64 bars. So that is where we find the baby boomers. All right, now when working with histogram, there's an understood order to the data listed on the horizontal axis. This allows us to once again consider the skew of a data. Now, consider the graph above. How would you say this data is skewed? Now, you remember that? If I draw that, what will you say? So this is skewed what? Right, because it falls towards the right. So this is skewed right. You remember we said that when the mean, so we said when the mean is less than the median, this gives us a left skewed. And when the mean is greater than the median, we have a right skewed. Okay, and then the third one, when the mean is equal to the median, which is also equal to the mode, we have symmetrical. Okay, and we are going to talk about it as the normal and then the bell-shaped. So this guy will be our focus right here. This guy right here will be our focus for the normal distribution. Okay, nice. Now, data can be distributed in many ways. Recall that data can be skewed left. So here, when you look here, because it falls towards the left, this is left skewed. So this right there is left skewed. So this is left skewed. And then because this falls towards the right, we say this is right skewed. Okay. Now the pattern here is unclear, right? We are not sure. Okay, so that is uneven. So this is left and that is right. Okay, nice. Now, the normal distribution, there are many cases in which data is symmetrical with most values clustered in the middle and fewer values on the low end and high end. So this is it. So you realize that this is symmetrical. Okay, now when I break that into two, okay, and I fold that together, I'll get even, right? There will not be any overlap. Is that okay? So this kind of data set is what we call a symmetrical data set. So in fact, when very large amounts of data are collected, the data will often start to form a bell-shaped curve. Now in this graph, a perfect bell-shaped curve has been overlaid on the data. This perfect curve is what we call the normal distribution curve. So this guy is what this will be our focus. Okay, the normal distribution. When you're talking about the normal distribution, we are talking about the bell-shaped curve, and that will be the focus. of our discussions for this particular section. Is that okay? Nice. So normal distribution is very important when it comes to data analysis, okay? And we are going to realize that we're going to come across a lot of industrial applications, okay? And even exam or classroom applications. And this has wide application in what we call the Six Sigma and data science and what have you, okay? So it's widely applied in many areas. Now, the normal distribution. Now, in this section, we will be studying the characteristics of the normal distribution because the actual data set is assumed to be close to perfect normal distribution curve. We can use these characteristics to analyze the data. So the characteristics of a normal distribution, the mean is equal to the median and also equal to what? The mode. Now, symmetry about the center. So the symmetry about the center. So this is the symmetry, axis of symmetry about the center. All right, we have 50%, okay, less. So this half 50%, and the other half is what? 50%. So the whole area under the normal guy is what? 100%. Okay, nice. So this is the normal guy, and the whole area under this is 100%. Okay, so 50 left, and then 50 to our right. Nice. Now let's look at the birth weight data. Okay, and let's do some analysis. Now the histogram of the sample data is the estimate of population of birth weights in newborn babies. Now the population distribution can be estimated by the superimposed smooth or bell-shaped curve. So this is the superimposed smooth bell-shaped curve. Okay, now we often infer from a sample whose histogram has the approximate normal shape that the population will have exactly or near as makes no practical difference. Okay, so here, let's look at this. So we're going to look at the, this is a real data set, statistical distribution in 2006. Now, what does the height of the bars of the distribution represent? All right, so the bars represent what? Frequencies, okay? And number of babies born at a certain birth weight category. And what do the weights of the bars represent? Equal intervals of birth weight ranges, right? Would you say the bell-shaped curve is skewed left or symmetrical? Is skewed or symmetrical? And we could tell that this is a symmetrical data, right? Now, what is meant by the distribution of the birth weight? So this is very important. And when we talk about distribution, we mean the different heights of the bars. So different heights of the bars is what we call distribution, how the bars are distributed, okay? Or how the weights are distributed on the graph. And that's what we call the distribution. All right. Now, this is leading us into a conversation, okay, about what we call standard deviation. Now, the graphs below represent 100 years worth of data on three cities temperatures in September. All graphs use 3,000 data values. Okay, that's a lot. And all three cities average 70 degrees Fahrenheit. Now, we're talking about Austin, September temperature, Indy, and San Diego. Okay, now this is, I've already mentioned that this is leading us into the conversation about standard deviation, and let's go straight and look at it. Now, are all these normal distribution curves? Yes, approximately normal, right? Because you don't see skewness, any form of skewness, so this is approximately normal. Now compare the graphs. How are they same or different? So though they are normal, they all exhibit normal distribution, right? But how are they same or different? Now, all the distributions follow a bell-shaped curve centered at the average or at the center. The width and height of the curves are different. Could you see that? You realize that the width and the heights are different, how they are spread out differ from each other, indicating that the data is spread out differently. Could you observe that? Okay, good. Now, and that is what we mean by standard deviation. Every normal distribution is described by its mean and the measure of a spread. So every normal distribution is measured by its average, and we are going to represent the average by this symbol we call mu, and the standard deviation we call sigma. And we will come across these symbols, okay, soon. Okay, so the standard deviation is a calculated value that indicates how much data set deviates from its mean and average value. A curve with a larger standard deviation will have more spread out data, while a curve with a smaller standard deviation will have data clustered closely around the mean. So the larger the spread, the larger the standard deviation. And then the lower the spread, the lower the standard deviation, period. Okay? Now, we want to rank these cities, Austin, Indy, and San Diego, in terms of temperature variability, which has the most variation. Look at the three graphs and tell me which has the most variation. And when you have done that, look at the same graphs and tell me which has the least. And what would this mean for their standard deviation? What do you think? Okay, so which has the most variation? Did you say Indy has the most variation? All right. And San Diego has the least. Okay. Mind you, we have said that the larger the spread, the larger the standard deviation. And then the lower the spread, the lower the standard deviation. And we know Indiana temperature is bipolar, right? It's cold right now. The next moment it's raining and it's hot, you know, so that's right. So this is a bonus slide. Freeman Matthew, a visual comparison of normal and paranormal distribution, Journal of Epidemiology. So normal distribution have wide application in epidemiology, right? You've seen talking about the curve. Have you heard about regarding the coronavirus, the curve and everything going on? All right, good. So in this course, you would either be provided with a standard deviation or you'll be given a set of data and use Excel to find the mean and standard deviation. Now, look at the example on birth weight. What are the given values for the mean and standard deviation? Now, the mean and the standard deviation have been given, and you see that. So the mean is this guy, standard deviation is this guy, okay? So for this class, you'll be given these values will be given to you. Now let's look at this application. All right, now below is a graph of normal distribution curves with the same mean, but different standard deviations. So we have this representing spring and that representing fall. Okay, and these are course grades. Okay, now let's see which curve appears to have a lower standard deviation. Tell me about it. The larger the spread, the larger the standard deviation. The lower the spread, the lower the standard deviation. So which curve appears to have a lower standard deviation? A lower standard, did you say spring? Right, if you said spring, that is right. Most values are closer to the middle for spring. So spring has a lower standard deviation. In which semester did students receive more Fs? In which semester did students receive more Fs? Look at the two. Is it in spring or in the fall? Spring or fall? Did you choose fall? Okay, fall, right? Scores are more spread out because look at fall. They are spread out. So we had a lot more receiving Fs in fall. Now, when were more C's earned? More C's. You had a lot of C's. When was that? When were more C's earned? And did you say spring? Right. So it had a huge number of people within that. Okay. Sweet. So that will give us a peak. So now we know what a standard deviation is. All right. And we already know what mean is. Exactly. We know how to find the mean. Now, the standard deviation is found by this. But for the purpose of this class, the standard deviation will be given to you. Okay. And you don't have to use this particular formula. This is by hand, and you don't need to use that. Now, I'll show you quickly how to use this, how to use Excel to find the standard deviation. So we already know that, right? Equal sign the average, and then you select the cells that you need to find. And then this is how you find the standard deviation, the command. So this gives you a step-by-step approach into how you can find the standard deviation and even how you can find the average or the mean. Okay, nice. So basically, this is all I wanted you to know regarding distribution. All right, the normal distribution. So this is an introduction, and I'll see you again in a short while for us to talk about the slide you see. That is the empirical rule. Okay, the empirical rule. Okay, so thanks for your time. And I will see you soon. Bye-bye.